terminal and close the existing emulator image that I had. Then I will launch the newly created emulator image using the same command as before, but this time instead of API34, I will use the name test device 1, and this will launch the AVD that we created right now. During first load, this could take a minute or so. If in your case, you're not able to use the emulator command directly from your command line, you have to make sure that your environment variables are set properly. To do this, head over to your Android Studio, click on Settings, and make a note of your actual SDK path in here. I just copy this and head back over to my terminal. To add the emulator and the platform path to your default environment variables, you can use the command export path equals to your path to your SDK. Your emulator is going to be present inside a folder called as /emulator. Follow it up with the existing path that we have. This will make sure that you can actually access the emulator binary from your default path. Also make sure platform tools is added to your environment variables. To do that, you can use export path equals to your same SDK folder, but this time follow it up with platform-tools. This is where you can find ADB and all of those utilities. Follow it up with $path. Now, when I do which emulator, it should point to your default emulator path that you just set up on the laptop. Make sure to set both of these up before you proceed to the next step. Next, we can use the utility root AVD to root our Android emulator. Root AVD streamlines your rooting process by automating a bunch of tasks that would otherwise require manual manipulation of your file system, of your system images for your emulator, and a lot of different things. If you want to see how root AVD accomplishes the rooting task, you can head over to the rootavd.sh and that will tell you all of the operations that are being performed in the background when you run the root AVD command. Let's try it out ourselves. I'll just copy the link over here, head over to my terminal, and I'll just do git clone root AVD. Next, I'll just head over to root AVD. Here you can see all of the required files that we need. In our case, we'll be using the rootavd.sh because I'm on a Mac M1. You can use the command /rootavd.sh list all AVDs, and this will list out all of the AVDs that can actually be patched on your file system. In our case, we know that we are targeting API 34, so I can just do a simple grep for 34 in here. When I do that, I'm automatically prompted with my RAM disk image. And this is literally the command that we will use right now to root our Android AVD image that we just created. So I'll just copy this and I'll run this as a command. When we run this, in the background, now your Android emulator image is going to be modified to gain root access on the file system. You will notice that the device automatically restarts during this process. You might notice a pop-up like this. All you have to do is make sure you are doing a cold boot. So I'll just do no for this. Now once the device is turned off, you just have to launch it again, and this time you should actually see a rooted image. Now you just have to restart the emulator image. Now you just have to restart the emulator image using the same exact command that we used before. This will launch our emulator image for us. Now, once the device launches, you should see an application called as Magisk installed on this device. This sort of confirms that the device is actually rooted, but before we proceed, we have to do a couple of things every single time. Head over to Magisk, click on Allow Notifications. You have to click on the update button corresponding to the app that you see over here. This will download and install the latest version of Magisk on this device. I'll click on Update again, and I'll click on Install. Now once the Magisk application is updated, launch it again. Now you will get a pop-up saying it requires additional setup. Click on OK. Click on Direct Install Recommended and click on Let's Go. Once the setup is complete, click on Reboot and this should reboot your device into a rooted state. And this time everything should be working well. Now once the device is loaded, to make sure that our setup is working well, I'll just head over to ADB shell and run the command su. When I run the command su, I can see a pop-up from the package manager over here. I can select forever and click on grant, and my application will get super user permission. In this case, I use this process to get super user permission inside ADB. Because we saw the pop-up for a package manager, this means that the rooting process should be working well. Now, to confirm if a custom application can request for escalated privileges on this device, we can take a look at the Frida Loader application. Let me install it to the device. I'll do this using adb install -r-g-t fridaloader.apk. Now, if the process worked when I launched Frida Loader, unlike the last time where the application crashed, this time it should launch well. Let's try it out. I'll launch Frida Loader. Application loads. I get a pop-up saying the application requests for super user permission. I'll click on grant. Once I click on grant, it says Frida Loader was granted super user permissions. Then to install the Frida server to the device, all I have to do is click on the install and run latest Frida server button. This will download and run the latest version of Frida Loader on this emulator image. This application uses a lot of su commands in the background, and that is why a rooted emulator image is mandatory for this application. Now we can see that Frida server is running on this device. So a quick recap. In this module, we learned how to create a new Android emulator AVD image and then root it using root AVD. A rooted Android emulator makes the process of testing seamless. To view the AOSP source code, you can use the standard web browser and head over to this link over here. So the link that you will be visiting is going to be on cs.android.com/android/platform/super project. In our case, we are targeting the Android 14 AOSP build, so let's make sure that we have selected the Android 14 QPR3 release from the drop-down over here. So this is going to be your repository root. The root directory is the entry point containing several important scripts and directories. Let's try and understand the folder structure for AOSP and the directories that we see over here. The first directory that we will be looking at is going to be the art directory. This directory contains the source code for the Android runtime, which is the managed runtime used by Android applications. Android runtime, which is also called as ART, replaces Dalvik and provides ahead of time and just-in-time compilation. It also provides garbage collection and other runtime services. The AOT and JIT, which is the ahead of time and just-in-time compilation, is managed by the ART compiler, and if you want to see the source code for it, all we have to do is open the ART folder over here, and here we can find the directory called as compiler. Once inside the compiler folder, you can see a bunch of different files over here. The first one that we will be looking at is going to be the android.bp file. This is basically a blueprint file that is used by the Android's build tool to describe how to build the compiler and the related components within the ART project. It basically defines the source files to compile, the dependencies, the build target, and the flags to be used. We can open this file to take a quick look at this. Here we can see that the complete file declares all of the information that is required in terms of a blueprint file for the build tool. This structure is going to be very important while building the project. If we scroll down, we can also see the list of dependencies that this file relies on. Then we have a file called as cfi_test.h. This file defines the tests for the control flow integrity inside the compiler. We'll talk about CFI elsewhere in the course in detail, but in short, CFI is a security feature that ensures that the program flow control follows a legitimate path. Basically, its goal is to prevent exploits such as control flow hijacking. Then here, there's a file called as compiler.cc. This compiler.cc file is the primary implementation file for the Android runtime compiler. It contains the core logic for compiling the DEX bytecode into the native machine code. In addition to these files, you can see a few other test files here. For example, there is an exception_test.cc. This one validates the correct handling of exceptions by the Android runtime compiler. Then we have the compiler_reflection_test.cc file. This one validates the compiler's handling of reflection. If you look at some of the directories that are present inside this path, the first one is going to be the debug directory. This debug directory contains the files that are related to the debugging support within the Android runtime compiler. For example, you can see the elf debugwriter.cc. You can also see files like debug.info and the elf symbol tab writer. Let's go back to the previous folder. Next, we can see a directory called as dex. This directory contains the functionality for handling Dalvik executable files, which is the bytecode format used by Android. Then, in the JIT directory that we see over here, you can find the implementation of the just-in-time compiler for Android. The files that we will be most interested in over here will be the jitcompiler.cc and the jitcompiler.h. Then we see a directory called as JNI. The JNI directory will tell us about the Java native interface interaction.